Hello everyone. In this video, we are going to design the beams under the applied loads, including the following key points that we need to cover step-by-step process for calculating loads, constructing the shear diagram, and determining the maximum factor design moment, and beam design with emphasis on tension steel reinforcement. So let's dive with our problem. Design beam for the applied loads as shown in the figure below. The beam has a cross-section of 300 by 600 mm using normal weight of concrete with strength of concrete which is equal to 28 megapascal, a reinforcing steel of 420 megapascal, and a unit weight of concrete which is 24 kilonewton per cubic meter. So as you can see here, there we have the load diagram and we are given the set of loading that consists of dead load and live load, concentrated load, and we have the uniformly distributed load which is 30 kilonewton per meter and 20 kilonewton per meter with a span of 6.5 meter beam. So we are giving these basic parameters Fc prime and Fy, and the unit weight of concrete which is 24 kilonewton per cubic meter. So the solutions, first of all, we need to determine the load, and this loading, we need to convert it into factored load so that very easy for us to manipulate to draw the shear diagram. So first of all, that is equal to Pu1 1.2 times the dead load of 27 kilonewton plus 1.6 times 18 kilonewton, that is equal to 61.2 kilonewton. So for Pu2, which is this one here, that is equal to 1.2 times 12 kilonewton plus 1.6 times 8 kilonewton is equal to 27.2 kilonewtons. And that is for the concentrated load. And for the uniformly distributed load, we have a 1.2 times the dead load, which is 30, plus 1.6 times 20, which is live load, and is equal to 68 kilonewton per meter. So now we have the load diagram, which is already converted into factored load. So first of all, we need to determine the support reactions from point A and B. So we will sum up moment either at point A or B. Let's say summation moment at A is equal to 0, positive clockwise. So for RB, that is negative because it is counterclockwise, times 1.5 meters, that is the moment arm, plus 61.2, that is for the live load, times the moment arms of 2.5 meters from here to there, and that is clockwise, so positive. Then another concentrated load, which is 27.2 kilonewton times 4.5 from here to there, clockwise, positive, plus 68 times 4.5 meters squared over 2, which is this one here, the uniformly distributed load. And that is clockwise, so again it is positive, which is equal to 0. Now for solving RB is equal to 148.3 kilonewton. So we have determined the RB, so now we can determine the RA by summing up forces positive upward is equal to 0. So and that is 148.3, that is reaction from point B, plus RA minus 61.2 kilonewtons because it is downward, so negative. So minus 27.2 downward negative, minus 68 uniformly distributed load times 4.5, that is negative, equal to 0. So RA is equal to 246.1 kilonewton. Now we have determined already the reaction at the support. We can now proceed to draw the shear diagram. So to draw the shear diagram, so first of all, we start at shear at point A, which is equal to the reaction at point A, 246.1. So the shear at point C, that is equal to the shear at point A minus the load between A and C, and that is BC is equal to 246.1 minus 68 times 2.5, and that is equal to 76.1 kilonewton. So that is the shear at this point here, just to the left of point C. Now at point C, between A and C, the only load that we have is 68 kilonewton, which is uniformly distributed. So in the shear diagram, it is linear if we have the uniformly distributed load. Now, the shear at point C, which is equal to 76.1 minus the concentrated load of 61.2, and that is equal to 14.9 kilonewton. This is the shear just to the right at point C. So at the shear at point D, again, is equal to the shear at point C, which is 14.9, minus the load between C and D. So the only load that we have in this region here between C and D is equal to 68 kilonewton per meter times 2, which is equal to minus 121.1 kilonewton. So again, at point D, we have a dropping load of 27.2 kilonewtons. So this minus 121.1 minus 27.2, that would give us minus 148.3. So the shear at point B is equal to negative 148.3 minus the load between D and B, but we don't have any load here, so our shear diagram is constant from D to B. But at point B, we have a positive reactions equal to 148.3, so minus 148.3, and that is equal to 0, and it has to be equal to 0, meaning the system is in equilibrium. Alright, we are done with the shear diagram. So before we calculate the maximum design moment, we need to determine first the location of zero shear, because that is the location of our maximum moment. So to determine the location of zero shear, we need to calculate the value of x by ratio and proportion. So 14.9, this one here, 14.9 is to x, similar triangle, is equal to 121.1, this one here, over the length from here to there, which is 2 minus x, so x is equal to 0.22 meters. So now the maximum area is equal to the area under the shear diagram. And this area consists of the trapezoidal plus the triangular, which is a small triangle here. So to calculate the maximum moment mu, that is equal to 0.5 times the baseline of the trapezoidal area from here to there, which is equal to 2.5 times the average height of the trapezoidal area, which is 246.1 and 76.1, not this one here. So that is 246.1 plus 76.1 plus the area of the small triangle here, that is 0.5 times 0.22 times 14.9, and the total area is equal to 404.4 kilonewton meter. So that is our maximum maximum moment located at the zero shear. So now we will check the minimum depth of the beam based on the ACI code, table 9.3.1.1, and this is the table. So for simply supported beam, we have L over 16. So for simply supported beam, H is equal to L over 16, that is 6.5 meters over 16, that is equal to 0.406, which is less than to 0.7 meters, the one that we have assumed the depth of beam. So we are greater from greater depth from the minimum requirements, so we are complied. So our depth is okay for this one. So beam self-weight is already accounted in the dead load calculation, so we don't have anything to worry about the dead load or the self-weight of the beam. So now we will determine the tension steel reinforcement. So first of all, we need to determine the steel ratio ρ using the given formula below. First of all, we need to assume that tension control, so that Fs is equal to Fy and P is equal to 0.9. So we need to assume this parameter so that we can use the formula. First of all, we need to again assume the effective depth, which is equal to 700 minus the clear cover, which is 40 mm, minus the centroidal of the center of the main reinforcing bars. Let's say we will use 25 mm diameter, and that is equal to 648 mm. That is the effective depth of the beam. So now if we use this, we have here the general equation of the moment, and if we substitute the rho on this equation, we will come up the quadratic equation. So rho, we have this formula. In order to determine the steel ratio, we need to determine first the value of M and Rn. These are the two parameters of this equation. So M is equal to Fy over 0.85 Fc prime, that is equal to 420 over 0.85 times 28, that is equal to 17.65. So for Rn, that is equal to mu over Pbd squared, is equal to 404.4 kilonewton meter times 10 to the power of 6 all over 0.9 times 300 times the depth, which is 648 squared, or equal to 3.57. That is for Rn. So now we can determine the value of ρ by substituting all these parameters to this equation, and we have 1 over 17.65 times 1 minus the square root of 1 minus 2 times the m, 17.65 times the Rn 3.57 all over Fy, which is 420. So to calculate the value of rho, and that is equal to 0.00926. So now we need to check also the minimum requirements as per the ACI code. That is section 99612. So 1.4 over Fy is equal to 1.4 over 420 megapascal is equal to 0.0033, which is less than to 0.00926. So we are okay because we are above the minimum requirements. There's another provision which is 0.25 times the square root of Fc prime over Fy, and that is equal to 0.25 times the square root of 28 over 420, that's equal to 0.00315. Again, it's also less than. We are also less than with minimum requirement. So the steel reinforcement is equal to rho BD, which is equal to 0.00926 times 300 times 648, and that is equal to 1800 mm squared. So if we use 25 mm diameter bars, it requires 4 pieces, and the total area is 1964 square mm, which is greater than to our minimum, greater than to our requirements, which is 1800 square millimeter mm. So now this is the beam section. We have 4 25 mm diameter bars, bottom bars. So this is the profile, and we are not calculating the top bars. This is the hanger bars. Now we have the stirrups. So we check the tensile strain. We need to check the tensile strain of the steel, just to make sure that the one that we have assumed is tension controlled. So to calculate the tensile strain, we need to determine first the value of A, which is equal to ESF times Fy over 0.85 Fc prime times B, which is equal to 1964 times 420 over 0.85 times 28 times 300, that is equal to 116 mm. So that is the stress block of the concrete. So C, the value of C, which is the location of our neutral axis, equal to A over B, is equal to 116 over 0.85, and that is equal to 136.5 mm. So by ratio and proportion, this is the equation. After simplifying the ratio and proportion of this triangle here, so that is 0.003 times D minus C all over C, and that is equal to 0.003 times 648 minus 136.5 all over 136.6 at 136.5, and that is equal to 0.0112. So here this is greater than 0.005, meaning that is tension controlled. So our assumption of Fs and P are correct. So that's all, guys. That's the end of our video for today. And if you enjoy this video, please don't forget to like or consider subscribing so that you will be updated for the next upload. So thank you for watching. See you next time. Bye bye and God bless.